Hey, this is Daniel Peters for ME308. This is my experiment. I'm going to be testing thermal time constants and boiling point elevation. Okay, so I didn't have a scale, so I basically had to make one out of this tray right here. Some dental floss, so I'm going to measure it in newtons. See, I've got it on the lower range right here. I'm going to calculate the mass in grams by dividing it by the gravitational constant and converting it to grams. Okay, so I measured the salt here. It turns out to be about 58.2 grams, so that's the number I'm going to use for my calculations. Here are my values for masses of salt that I'm measuring. Each of these should give a different molality of the solution. You can see my calculations on there. Each one should raise the boiling temperature of the water, and I assume that it will increase the time constant and cause it to maintain heat longer. Okay, so I just measured 1 kilogram of water right here. Measured the ambient or room temperature in here. It's about 23.5 degrees Celsius. So now I'm going to try the pure water solution and boil that and see it should come out to 100 degrees Celsius. I plan putting this to about number 6 or 8. Actually, I think I'll try putting it to 8. I should do that every time, and hopefully I'll get the same results. Okay, so right now it's still boiling, but I'm graphing the temperature as it boils. This is the pure water right now, so it should be 100 degrees Celsius, hopefully. Took all the data points, but and this is all for the first run without using any of the saltwater solutions. It's all done in this pot right here. But this is from when it's heating up, and then this is when it's boiling. This is after I took it off. Started cooling. I timed it out, so I had to start some new runs. It just cool exponentially, but keep in mind that these are in seconds, so this experiment is over 2 hours long. Just for this run, so I'm gonna have to shorten that up a bit. For this area right here, it kind of go all over the place, so the average from right here is about 98.5 degrees Celsius, so that's what I'll use for my boiling point for the water, just the pure water. FFT graph of the 5th run from the 0 moles per kilogram solution, or just the pure water. And every single one of these, it peaks at 0, but when I take a sampling frequency closer to the aliasing frequency, since I see a little peak right here, I think I'm going to change the sampling rate to 4 samples per second, because I had it at 30 samples per second before, and yeah, that was just a bit excessive and a little bit much on my computer, so we'll try that and see what happens. Okay, so looking at this graph, you can see that there's a couple places right here. We're probably going to mess up the data, so I'm just going to strike through the data. Okay, now I've struck through some of the outliers, and it's has a much cleaner graph now. So there's a little bit of stuff around here. Okay, so this is the 1.5 moles per kilogram solution, and I'm stirring it in right now to 1 kilogram of water. Measured it, and it was about 9.814 newtons, which means that the amount of water in there was 1 kilogram. And that's adjusting for the tare weight, of course. Okay, so this is the 1.5 moles per kilogram solution, and it's currently cooling right now. I have it set to stop after it's been cooling for 20 minutes, but I have the whole time set to 21 minutes because I let it boil for a minute before taking it off the heater, and then I let it cool, and I have it put in place and set in one specific spot to avoid any uncertainty due to cooling by convection. Right now I'm measuring the ambient temperature, or the room temperature, for the 1 mole per kilogram solution. This is how I'm going to determine the boiling point right here, by averaging this out. Okay, so for my pure water, I'm using this value right here is the initial temperature. Is about 97.6 degrees Celsius. Okay, so for the 2.5 mole per kilogram solution, this is how I'm doing the linear regression, taking the natural log of the temperature and the ambient temperature over the initial temperature minus the ambient temperature, and I'm taking the absolute value of that in case any of the differences become negative. Here are the results from my lab and the data I collected, and here's the uncertainty analysis of the mass of the water and the salt based off the uncertainty of the thermocut of the dual range force sensor. And here in this section have all the graphs of the temperature versus time, and like the one below it is the natural log of the temperature minus the ambient temperature over the initial temperature minus the ambient temperature. As you can see, for this one I took measurements as it was boiling and heating up, and then as it was cooling as well. I took this at 30 samples per second, which was a bit much, so for the following experiments changed it to about 4 samples per second, which may have also affected the time constants I got from there. And after looking at everything, I never actually saw a trend in the time constants because there's too much uncertainty. But I think that, and also considering that the temperatures of the uncertainty of the thermocouple is greater than the temperature difference between two concentrations of solutions. So had I taken more accurate measurements, I probably would have seen the time constant decrease with increasing solution concentration, because it would take longer to reach ambient temperature that way. And thank you for watching my presentation.